When we selected models by stepwise regression, we took each step and looked at whether or not that new degree of freedom improved the model with statistical significance. Now, you can't always do that, but there are other ways that you can select what might be the best among a choice of different models. One of the most famous, best known, and perhaps most often used is something called AIC, which stands for the Akaike Information Criterion. It's based on estimating the likelihood of the model fit, and then taking into account how many parameters the model has. If we have a model fit where the fit has a likelihood L, when it's using K parameters, the Akaike Information Criterion is -2 times the logarithm of L plus 2 times K, the number of parameters. When you compute this, the best model, or at least the likely best model, is the one that has the lowest AIC. That's because it rewards models which fit well. When the likelihood L goes up, so that negative log likelihood goes down, the Akaike Information Criterion goes down, meaning better model. It also penalizes models with more parameters. When K goes up, AIC goes up. The whole idea is that a model is better if it fits better, so it has a greater likelihood. It's also better if it's a simpler model, so it has fewer parameters. Now, there are other information criteria besides AIC. Of the others, the best known is the Schwartz Information Criterion, also known as the Bayesian Information Criterion, often called BIC. The difference between BIC and AIC is that BIC penalizes additional parameters more severely than AIC does. Let's go through and try again the polynomial fits for degrees 1 to 10. But this time, let's compute the AIC, Akaike Information Criterion, for each model, and plot how AIC changes as a function of polynomial degree. Well, here we see that the lowest AIC value is for polynomial degree 3. As we get a higher and higher polynomial degrees, we get higher AIC values, which means not as good models. So AIC also indicates that a polynomial of degree 3 is the best model among these choices, low-order polynomials. That agrees with what we got from using p-values computed from the fits themselves. So in this case, the two ways of selecting a model happen to agree. Now, the model with the lowest AIC is the cubic, as we got before. But one estimate, something to be aware of is, when you're comparing different models with AIC, they'll have different AIC values, and the lower AIC value means probably a better model. But suppose AIC was only lower by a tiny amount. That means that the two models don't really have that much difference in how well they fit. There is an estimate of how much better one model is than another. Take the difference between the AIC values for the models. Then estimate the ratio of their chances as the exponent of negative difference over 2. That means that if the difference is 1, then the relative likelihood is e to the minus 1, which is something like 0.4. So one model is more likely, but it's not overwhelmingly more likely. It's certainly not a sure thing. If the difference in AIC is 100, then the relative likelihood of the lesser model, or the less likely model, is e to the minus 50th. That's pretty close to impossible. So the difference in AIC can be used to compute how much more likely is one model than the other. Another thing to be aware of is AIC is not infallible. The Bayesian information criterion isn't infallible. Nothing's infallible. Stepwise regression is far from infallible. Something to be especially keenly aware of is information criteria like AIC are dependent on computing the likelihood of your model. The likelihood of your model, when you pump it through your computer software, it computes it based on the assumption that the noise is white noise. If the noise is not white noise, then the assumption behind that computation doesn't hold, and the AIC calculation you get from your computer program will not be correct. You can still compute AIC, and you can still use it, but you'd have to do a more complicated calculation, which takes into account that the likelihood depends on autocorrelation. So when the noise is autocorrelated, when it's not white noise, the usual estimates, which are based on white noise assumption, can't really be relied on. The bottom line is use some common sense. When I'm in doubt, when things are close, when I'm not sure, when something looks fishy, I tend to have more confidence in simpler models than more complex ones, and simpler usually means those that have fewer parameters. One last thing I'd like to mention, and that is that when you have a small sample, or even in all cases it's a good idea, there is a correction to AIC leading to AICC, the AIC corrected, if little n is the sample size. The corrected AIC is the same as the old AIC plus this correction term. It only becomes important for small samples, but even for large samples it's still a valid correction. Some people like to compute the corrected AIC all the time. Some people even recommend it. I think it's okay to use ordinary AIC unless you have a small sample size. In particular, the sample size should be at least as big as the square of the number of parameters if you want to be able to rely on AIC.